So, dear students, this is a question that is dealing with. We have a DC machine, and in this question, we will be calculating the machine constant, and we will be determining the internally generated voltage and the currents in the coil and these things. So, for a DC machine, as it is in our knowledge, is that a DC machine is composed of, we have the stator and we have the rotor. And for the rotor, a rotor has windings over it, and the stator has magnetic poles in it, right? Two pole, or we can have a four pole machine. Now for the rotor, for the armature side, that is the rotor, the windings are of two types, and these windings are referred to as lap winding or wave winding. So the critical formulas for the machine constant Ka is actually equals to Z. Z is the total number of conductors, and P is the total number of poles. Z is the total number of conductors, and we have also a critical constant that is actually calculated on the basis of the type of winding that is in the machine. So for the lap winding, let's consider our case. What is our case? Determine the armature constant Ka for a lap wound machine. Now, if you remember, lap wound machine is actually if it starts, turns, and it ends at the neighboring side. The next one will start and it will lap and it will end on the neighboring side. So they are overlapping. So for this kind of machine, A equals to M of P. The value of A is M of P, where P is the number of poles, that are 4, and M is a constant that is determined by the type of winding. If it is simplex winding, M equals to 1. If it is duplex winding, M equals to 2. If it is triplex winding, M equals to 3. This actually determines how many overlaps exist at one time for one pole. So we can calculate to calculate the machine constant, A equals to M of P, and rest is here. So and what is Z? Z is the total number of conductors. So for our scenario, there is the 4 pole machine, and it has 33 coils, each coil having 7 turns, and the coils are accommodated in 33 slots. That are 33 coils in 33 slots. So what will be the value of Z? There are basically 33 coils. There are like this 33 coils, and actually each coil has 7 turns. So total number of conductors 7, have 7 turns, and each turn has 1 and 2 conductors into 2. So in this way, the value of Z will be equals to 462. Now P for our machine, the value of P for our machine, it is a 4-pole machine, so P is equals to 4. Now the value of A is equals to M of P. It is lap wound, or we can say that they have not mentioned it to be a duplex or triplex. So the value of A will be A equals to MP, that is 1 into 4 equals to 4. Now these values are strictly for lap wound, overlapping type of coils wound machine. So if these are all the values, so for the first part, determine the armature constant. We can calculate Ka equals to Z into number of poles upon 2 pi A, and we have calculated the value of Z to be 462. It is a 4-pole machine. We have 2 into pi into A, we have calculated to be 4. So this will become, the value of machine constant will be Ka equals to 73.53. Now the second part states as determine the induced armature voltage when armature rotates at 1000 rpm. So the induced armature voltage is actually equals to Ka phi omega. So they have actually given us N mechanical, that is 1000 rpm. If we will convert it into radians per second, we can use this formula. The machine constant we know, but the flux is something that we have to calculate. Now, how to calculate the flux? Now, let's focus on this thing, and this is another tricky part that you need to understand. Not that tricky, but it requires mechanical dimensions. So armature is radius of our armature. So is this. So if we look into our diagram, the radius of our armature, which is cylindrical form, is actually 12.5 centimeter. And the next states the effective length is 25 centimeters. So the length, that is effective length, is equals to 25 centimeter. So rotor, the radius is 12.5, length is 25 centimeter, and the pole covers 75% of the armature periphery. So it is a 2-pole machine, a 4-pole machine. So when this rotor is inside, at one time, this is one pole and this is the other pole. It is both the poles, all the poles that are covering the machines. 75% of this machine area is under the effect of poles. That means the torque or the voltage that will be being induced, or the torque that will be induced on the rotor, is due to the electromagnetism that is only acting on 75% of the total area. Where is the other area, 25%? It is in between the gaps of the poles. So if this is the status of our machine, can we calculate the pole area, the total area? This is a cylinder. Can we calculate the area of a cylinder? If we can calculate the total area of the cylinder and we multiply it with 75%, we will get the effective area that is under the poles. The rotor cylinder, which is under the effect of the poles and which is producing the necessary EMF. So pole area, the effective pole area, we can calculate it. Pole area is actually the area of the cylinder. So the area of the cylinder we know is 2 pi RL over the number of poles. The effective area of the and this will be equals to 2 into 3.14 into the radius, that is 12.5 centimeter. We converted into meters, into the length. We again convert this into meters, divided by 4 and into 0.75, which is actually the effective area, 75%. So what will this become? The effective area of this will become 36.8 into 10 raised to power minus 3 meter square. Now, why are we calculating this? We should remember we have to calculate the flux. Now we have a beautiful formula. We all know that is known as flux density, flux over area of the pole. If we have the area of the pole and if we have the flux density, we can calculate the flux. So let's see if we have the flux density. The average flux density under each pole is 0.70. So the effective area that is under each pole, where the effective flux density is this, so the flux at that area will be flux equals to flux density into effective area of the pole, and this will actually becomes equal to what is the flux density? It is 0.75 Tesla into 36.8 into 10 raised to power minus 3. So flux will be 0.0276 Webers. So that is fine. Now we have the flux and the speed. If we want to convert this to radians per second, what should be the formula? Into 2 pi over 60. This was the formula to convert this into radians per second. And once you have converted this, then we can calculate EA, and EA will be 212.5 volts. This will be the induced voltage in our machine, which they have given us in the case of lap wound machine. Because how have we calculated this? If we have calculated the flux, and then we have the flux here, we have the speed here, Ka. Now this was calculated for lap wound machine. So we have calculated EA. Determine the current in the coil and the electromagnetic torque developed when the armature current is 400 amperes. So for the part C, determine the current in the coil and the electromagnetic. So the current in the coil for our machine is given as I coil equals to the total armature current divided by A. And A is this one that we have calculated. So this will actually becomes equals to the total armature current was 400 divided by 4, that is equals to 100 amperes. Right, this is the current in the coil. And then it asks about the torque. Now torque that is induced or the machine is equals to Ka phi Ia. We have calculated flux, we have calculated the machine constant, they have given us the armature current. So this will become equals to 73.53. Flux that we have calculated previously is 0.027 and I is 400 amperes. So the torque that will be induced over the coil will be 811.8 Newton meters. And lastly, determine the power developed by the torque. Now the power that is developed by the torque is being required. So the power developed by the torque, there are two ways that we can calculate the power that will be developed by the torque. Number first is if we can calculate the mechanical power, that is torque into speed, and this will be equals to 811.8 into, again it is in RPM, so we have to convert the speed, that is equals to 2 pi into 60, and this will be equals to 85 kilowatts. Or we can calculate it by the electrical power. The voltage to the induced voltage in our machine is EA and the armature current is IA. So induced voltage that we calculated was actually equals to 212.5. Here we calculated this voltage and the armature current is 400 amperes. So this will again turn out to be 85 kilowatts. So both, and as we have seen that the power that is converted inside the machine is actually this power, and we have not considered the losses that are occurring inside this machine. So all these this part was actually for our uh, overlapping type of machine, or we call it lap wound machines. Now let's look at the second. In the second part, if the armature is wave wound. Okay, so the B part says if the armature is wave wound. Wave wound is another type in which if this is the part of the commutator, it starts from here and it ends at the other side of the armature. So it is not, it is in the form of a wave, and the windings are not overlapping each other. So in this scenario, for the machine constant, what the thing that will only change will be the machine constant, and also the, so in this case number of poles are again 4, but for the value of A for wave wound machine will always be 2. It will not be MP, it will be 2. And the value of Z, as we have calculated previously, will remain the same. That is the total number of conductors that we calculated. And where did we calculate? Here we have calculated, they will remain the same. That is 462. So for this scenario, the value of machine constant changes and it will be 147.06, because its a construction is different, so the machine constant is different. Rest all the things that we have done will be same. For example, we have calculated the internally generated voltage. Now the machine constant is changed, flux will remain same and the speed will remain same, and flux you will calculate similarly by calculating the effective pole area. This is the same for the machine. And in this scenario, so the value of EA will be calculated to be the internally generated voltage 425 volts, 4 to 5 volts. So one of the important difference between lap and wave winding that can be seen is there is a clear difference in the induced EMF voltage that is higher, almost double. Similarly, in this case, the armature current for the parts C sorry, where it is? Here it is. The coil current will be 400 divided by 400 amperes, and the armature current for this scenario, IA is equals to A into I coil. Previously, this armature current was A into I coil, that was 4 into I coil. In this case, the value of A is 2 is fixed, so this is 200 amperes. So the induced torque will be Ka flux A Ia, and induced torque value can be calculated to be 811.8 Newton meters, and the power again will be 85 kilowatts. So the induced torque is same, the power is same. So what has differentiated? The thing that has differentiated in both the lap wound machine, a wave wound machine, was the amount of current that was being induced in the armature. And the effective current, in one case, the voltage induced was less, but the current was larger. So, if the winding size is same, then the copper losses in lap wound will be higher than the wave wound. But in the case of wave wound, the voltage induced was higher as compared to the lap wound machine. So I hope this helps. Thank you.